Hi, my name is Chris Robles. I'm a first-year student here at UCLA. Just finishing up my first year. I'm going to talk about a rotation project I did with Professor Sriram here, entitled "The Impact of Neanderthal Ancestry on Depression in East Asians." So first I want to talk about the theories of modern human evolution. The theories of modern human origin, sorry. So one big question is, did Neanderthals evolve into humans, or did they die out and get replaced by modern humans? So there's a couple models that are widely regarded, one of which is the multi-regional model. And this one says that there were waves of expansion from Africa of different hominids spreading all throughout the world, and they kind of mixed together, and this led to modern humans. The other model is the out of Africa model, which kind of says that mutation happened in Africa from Neanderthals, which led to these modern humans. Now, so recent research shows that maybe things are a little bit more complicated than these models. In fact, sequencing of Neanderthals has shown that 1 to 4% of European genetic ancestry is related to Neanderthals. And although most of these variants are deleterious in humans, some of these variants may be beneficial and may have provided an evolutionary advantage to these modern humans. So there's been previous studies that show a small but significant amount of heritability of phenotypes can be contributed from these Neanderthal SNPs. And so the question that we wanted to ask was, what is the effect of Neanderthal ancestry on phenotypes in modern humans? So the approach we wanted to use was a GWAS, and this gives us information on the variation in genome between people, and using Neanderthal informative mutations, which from here on I will refer to as NIMs. And however, there are some challenges with these approach when you're looking at NIMs, or Neanderthal informative mutations. One of these challenges is, where are these alleles in the human genome? So this has actually been addressed previously by some research, such as what was done by Professor Sriram. And so Sriram will be talking about this later on in the program, so I don't want to spoil too much for you guys. But just very basically, in order to identify a Neanderthal region in the human genome, a method was developed to look at several features of the genetic variation that are informative of the Neanderthal ancestry. And using this method, it would give us a set of SNPs which would tag Neanderthal segments in an individual's genome. So you can see here, there'll be certain features. This is our test genome, and we want to see whether a region came from Neanderthal or African ancestry, and then you can have your tag SNP within that region. Another challenge to using the GWAS to look at Neanderthal informative mutations is that a lot of these NIMs have low frequency, so they're very rare. And usually GWASs look at more common SNPs that have a minor allele frequency of above 5%, 0.5%. But this misses out on rare alleles, such as what's in these Neanderthal informative mutations. And so here's just a distribution of the data set that we use, which I'll talk about in a moment. And you can see that the minor allele frequency of a lot of these NIMs is very low. So our goal was to interrogate if the NIMs has an effect on the depression phenotype. And again, we did this because we were looking at some previous research done by Samanti in 2016 that was in 28,000 adults with European ancestry, and they used electronic health records to look at the phenotypes and say whether or not these individuals had depression or amongst other phenotypes. And actually in this paper they found that NIMs explain 2.03% of depression. And we wanted to see if we could extend this idea to another data set with a different population, since this was just in Europeans. So that led us to the Converge data set, which was done here at UCLA by Jonathan Flint, who also will be speaking later on in this program, so pretty exciting. And this data set had around 10,000 case-controlled matched individuals with major depressive disorder. And these were Han Chinese women from 58 hospitals in China. And we had phenotype information for recurrent depression and melancholia, which is actually it's like a more severe form of depression and more inherited from your family. And also we have records of the age, location, hospital, as well as the first 20 principal components. And and this also is one of the most comprehensive studies done on depression to date, so it's a really good data set. So first, to look at this, we wanted to look at single SNP associations. So we use logistic regression to calculate the association of single SNPs in both depression and melancholia phenotypes. And we used around 75,000 SNPs identified to tag the Neanderthal segments, the Neanderthal informative mutations I was talking about. And these were identified from East Asian individuals from the 1,000 Genomes Project. And so some of our results, here's just a Manhattan plot for those of you that don't know. It just shows the single SNP association with this is for the depression phenotype, and the x-axis shows the position along the chromosome, the genome by chromosome, and the y shows the p-value. And here is, in the black and gray, is all of our SNPs throughout the whole Converge data set, while the green ones represent those that are Neanderthal informative mutation SNPs. And you can see here, ignore the red line, but the blue line is where it would show significance when corrected for multiple testing. You can see there are some hits that show SNPs that are associated with depression, yet none of these are green, so none of these represent our Neanderthal informative mutations. And here's just a QQ plot showing the relationship between observed and expected. And we can see that everything looks good here. There's no unexpected associations. This is for the depression phenotype. And then again, we repeated this for the melancholia phenotype, which is a more severe version of the depression. And we can see that there are no significant associations for any of our Neanderthal informative mutations when looking at single SNP analysis association. And again, here's another QQ plot. So following that, we wanted to look at the genetic contribution to the phenotypic variance. And unlike using single SNPs, we wanted to provide an estimate of the variance by looking at the NIMs in total. And this is because single associations are problematic since just such a stringent p-value is used. And this may reduce type 1 errors, but it causes some significant associations to be missed. So we used our NIMs to compute a genetic relatedness matrix in our linear mixed model. And so if K is the genetic relatedness matrix in our linear mixed model here, we used the NIMs to calculate that, the Neanderthal informative mutations. And so we were able to estimate our heritability for major depressive disorder. And you can see here that there is heritability of around 1%, and we also use a disease prevalence of 7.5% in order to transform to a liability scale to adjust for assertion bias. And this is because in our data set it was 50-50 case control match. However, the disease prevalence is closer to about 7.5%. And you can, so in conclusion, we found that no single NIMS shows significant association with depression or melancholia phenotypes. Heritability of depression due to NIMS as a whole are not significantly different from 0, which kind of contradicts with the previous findings. And this leads us to believe that phenotypic impact of archaic ancestry is likely to vary from population between maybe Europeans versus Han Chinese individuals, such as in our converged data set. Yeah, and so for the future, I'm going to do stratification for the phenotypic variance, which just involves random draws of SNPs with the same minor allele frequency and LD scores that are Neanderthal informative mutations. And this will allow us to see if the heritability is significantly different from a random subset of SNPs in our data set. And so I want to thank Professor Sriram, Jonathan Flint, and Charleston Chang, who are with the Converge Consortium, and then my funding as well. Thank you.